Have you ever wondered what the strongest storm on Earth really looks like from space? And what happens when that monster begins turning toward the United States? This is not just another tropical cyclone. This is a super typhoon, powered by an ocean of heat, driven by forces larger than continents, and capable of reshaping entire coastlines in a matter of hours. Tonight, we follow its path, its structure, and the science behind the most extreme storms on the planet. Before we begin, please like the video, subscribe to the channel, and stay with us for the full story. The Earth turns steadily beneath a continuous flow of energy from the Sun. Across the curved surface, sunlight arrives unevenly, most direct near the equator and more slanted toward the poles. This uneven heating establishes a persistent contrast between warm and cool regions, and from this contrast the atmosphere begins its slow, global motion. Air warmed near the equator expands and rises, while cooler air at higher latitudes sinks and flows back toward lower latitudes. The rotation of the planet bends these flows, shaping them into broad wind belts that circle the globe. The combined effect of solar heating and planetary rotation forms a stable background in which storms can develop. Over the oceans, the influence of sunlight becomes stored in water. The sea absorbs heat during long daylight hours, and the upper layer remains warm, especially in regions where sunlight is strong and persistent. This stored heat does not remain still. It interacts with the air above, transferring warmth and moisture into the lower atmosphere. The ocean surface becomes a boundary where energy passes from water to air, supporting clouds, winds, and, under certain conditions, organized systems of rotation. In tropical regions, where the ocean remains warm for extended periods, the atmosphere often becomes humid and unstable. Warm air near the surface rises easily, carrying water vapor upward. As this vapor cools, it condenses into cloud droplets, releasing latent heat, which is the energy stored during evaporation. This release of heat reinforces the rising motion, allowing clouds to grow taller and more persistent. In many cases, these clouds remain scattered or loosely organized. In some cases, they begin to cluster, guided by subtle differences in wind and pressure. The Earth's rotation plays a quiet but essential role in this process. As air moves across the surface, it does not travel in a straight line. Instead, it is deflected, turning to the right in the northern hemisphere and to the left in the southern hemisphere. This effect, known as the Coriolis influence, allows areas of low pressure to develop rotation. Without it, rising air would simply spread outward without forming a coherent system. With it, the flow begins to curve, and under favorable conditions, a rotating circulation can form. Large-scale pressure patterns help organize this rotation. Over the oceans, broad zones of relatively low pressure can form where warm air rises. Surrounding these zones, higher pressure areas push air inward. As this air converges, it is forced upward, reinforcing cloud formation. The balance between inward flow at the surface and outward flow at higher levels creates a structure that can sustain itself, provided the environment remains supportive. Across the Pacific Ocean, particularly in its western region, conditions often align to support strong tropical cyclones. Warm sea surface temperatures extend over vast distances, and the atmosphere above remains moist and unstable. Seasonal wind patterns shift in ways that reduce disruptive forces, allowing storms to organize without being torn apart by strong changes in wind speed or direction with height. When these elements come together, a disturbance can begin to strengthen. At first, such a disturbance may appear as a cluster of thunderstorms. The clouds rise and fall, releasing heat and drawing in more air from the surroundings. If the rotation becomes more defined, the pressure at the center begins to fall. Air flows inward more strongly, feeding the system with additional warmth and moisture. The storm becomes more organized, with a clear circulation forming at lower levels. As the system grows, it begins to influence its surroundings on a larger scale. The pressure difference between the center and the outer environment increases, strengthening the winds. These winds move across the warm ocean surface, enhancing the transfer of heat and moisture into the storm. The process becomes self-reinforcing, with each cycle of rising air and condensation adding energy to the system. The global environment continues to shape the storm's path. High-pressure systems and prevailing winds act as guides, steering the circulation across the ocean. These steering currents are part of the broader atmospheric structure, extending over thousands of kilometers. The storm does not move independently. It is carried along within this larger flow, even as it maintains its own internal dynamics. In some cases, a tropical cyclone grows into a system of exceptional strength. When sustained winds reach very high speeds and the internal structure becomes highly organized, it is classified as a super typhoon in the Western Pacific. Such storms represent the most intense form of tropical cyclone, drawing vast amounts of energy from the ocean and releasing it into the atmosphere through continuous convection. Observations from satellites and ocean buoys indicate that these powerful systems rely on a delicate balance. The ocean must remain warm enough to supply energy, and the atmosphere must allow the storm to maintain its structure. If the environment changes, the storm can weaken. If conditions remain stable, it can persist for many days, traveling long distances across the ocean. It remains uncertain how individual storms will evolve in detail, even with advanced observation systems. While general patterns are well understood, small variations in temperature, moisture, and wind can influence the storm's intensity and track. These uncertainties are part of the natural complexity of the Earth system, where many interacting factors operate simultaneously. Within this planetary setting, the stage is established for the development of a powerful storm. The rotating Earth, the warm ocean, and the moving atmosphere create a framework in which energy can gather and organize. The system remains part of a continuous exchange between sea and sky, shaped by forces that extend far beyond any single storm. The scene remains broad and expansive, defined by global patterns rather than local details. The storm, though significant, is still one element within a much larger system. Its behavior reflects the underlying structure of the planet, where heat, motion, and rotation interact in steady, predictable ways, even as individual outcomes vary. The Earth continues its rotation, and within this motion, the conditions for powerful storms persist. The western North Pacific stretches across a vast part of the planet, larger than any other region where tropical cyclones regularly form. It lies between the eastern edge of Asia and the broad expanse of the Central Pacific, and within this space the ocean remains warm over enormous distances for much of the year. Islands, archipelagos, shallow seas, and deep basins interrupt the surface, yet the dominant impression is one of continuity. Water covers most of the region, and over that water the atmosphere often finds the warmth and moisture needed to organize long-lived storms. This basin includes the Philippine Sea, the South China Sea, the waters around Micronesia, and the open reaches east of the Mariana Islands. Farther north, the sea gradually cools as it approaches Japan and the subtropical belt. Farther south, near the equator, the winds and rotation conditions change, limiting cyclone formation very close to the equatorial line. Between these two bounds lies a broad corridor where the environment repeatedly supports the birth and growth of typhoons. The region is favoured not by chance, but by geography and climate acting together. Warm currents move through the basin, and strong tropical sunlight keeps the surface ocean supplied with heat. The sea surface often remains above the threshold commonly associated with tropical cyclone development, though that threshold is only a useful guide and not a strict rule. What matters more is the combination of warm water, moist air, and a background pattern of winds that can allow rising motion to persist. In the western North Pacific, these elements often coincide over large areas at the same time. Seasonal changes shape the basin without making it inactive for long. During the boreal summer and autumn, conditions usually become most favourable. The ocean has stored heat over many months. The atmosphere is deeply humid, and the large-scale wind patterns commonly support organised convection, which is the sustained rising of warm, moist air into towering cloud systems. The basin can still produce storms outside this peak period, but the clustering of ingredients becomes most reliable during those warmer months. The result is a long season with high activity and a tendency for some storms to reach exceptional strength. The western North Pacific also differs from smaller cyclone basins because its favourable area is so wide. A disturbance can begin far from land, move over warm water for many days, and continue strengthening without the interruption that continents often impose elsewhere. Long tracks across open water allow a storm more time to organise its circulation, deepen its central pressure, and refine its internal structure. This does not guarantee intensification, since many other factors remain important, but it increases the opportunity for growth. Within this basin, the monsoon trough often plays a central role. The monsoon trough is a broad, elongated zone of low pressure where winds from different directions converge. It is not a narrow line, but a shifting region of unsettled weather, cloud clusters, and embedded circulations in the western North Pacific. This feature can extend across a large portion of the tropical ocean. It becomes a breeding ground for tropical disturbances, many of which remain weak, while some gradually consolidate into named storms. The trough supplies a favourable background of convergence and rotation, helping small disturbances gather into larger systems. Humidity in the lower and middle atmosphere also helps explain why this basin is so productive. Dry air can weaken a developing storm by disrupting the steady rise of moist air and reducing the release of latent heat. In the western North Pacific, deep tropical moisture often occupies large volumes of the atmosphere, especially in the active season. This does not remove all barriers to development, but it reduces one of the most common obstacles. Rising air can continue upward through a deeper layer, supporting tall cloud towers and repeated bursts of convection. Another important feature of the basin is the relative distance from strong continental effects in many formation zones. Over land, surfaces heat and cool rapidly, mountains disturb the flow, and dry air can enter from elevated terrain or seasonal air masses. Far over the western Pacific, these interruptions are weaker. The atmosphere above open ocean tends to change more gradually, and the storm interacts primarily with sea surface conditions and large-scale winds rather than with rough terrain. This steadier environment can favour persistence. At the same time, the basin is not uniform. The South China Sea is smaller and more enclosed, with surrounding land masses that can alter wind and moisture patterns. The Philippine Sea, by contrast, opens into a much wider expanse of warm water and often supports stronger, longer-lived systems. Areas near the subtropics may provide a path for storms that have already formed farther south. while waters close to the equator generally lack sufficient Coriolis influence for full cyclone organization. Even when the ocean is very warm, each part of the basin contributes differently to the life cycle of storms. The western North Pacific is also a region where observation has improved greatly over time. Satellites monitor cloud structure, sea surface temperature, and moisture patterns across the entire basin. Drifting buoys and anchored instruments report conditions at the ocean surface. Aircraft observations are more limited than in the Atlantic, but remote sensing provides continuous coverage over wide areas. These observations indicate that the basin routinely produces more tropical cyclones in a year than any other on Earth. Though the exact count varies from season to season, it remains uncertain in advance how many storms any given season will produce, because large climate patterns can shift the environment in subtle ways. Broad climate oscillations can influence where storms form and how they travel. When sea surface temperatures and atmospheric patterns shift across the tropical Pacific, the favoured region for genesis, meaning storm birth, can move eastward or westward. Some years support more activity in the open ocean, while other years favour formation closer to the Asian side of the basin. These changes affect the average tracks and the likelihood that storms will threaten different islands or coastlines. Observations indicate these relationships clearly, though the behaviour of any individual storm remains dependent on local conditions as well. The basin also supports the development of very intense storms because it combines breadth, warmth, and time. A storm that forms in an isolated part of the open ocean may remain over favourable water for several days without encountering land. If upper-level winds allow efficient outflow, meaning the spreading of air away from the storm at high altitude, the central circulation can continue to strengthen. In this environment, the western North Pacific becomes the setting where some of the strongest tropical cyclones on record have been observed. Yet even in this favourable basin, development is never automatic. Many disturbances fail to organise. Some are disrupted by unfavourable winds aloft. Some ingest dry air. Some move into cooler water or interact with nearby weather systems in ways that prevent a tight core from forming. The basin provides opportunity, not certainty. Its importance lies in the scale and consistency with which it offers that opportunity. So the western North Pacific stands as the broad environmental cradle of the typhoon. It is a region of warm seas, moist tropical air, seasonal convergence, and long distances without interruption. Within it, the atmosphere and ocean repeatedly meet, under conditions that support spinning, rising, organized weather. The basin does not determine the exact form of any one storm, but it supplies the expansive setting in which such a storm can begin and endure. Across the western and central Pacific, the path of a powerful tropical cyclone is shaped by winds and pressure systems much larger than the storm itself. These broad patterns do not belong to the storm, though the storm moves within them. In the tropics and subtropics, air flows around sprawling areas of high and low pressure, and this larger movement acts as a steering current. A super typhoon may contain violent winds near its centre, but its forward motion usually reflects the quieter, wider arrangement of the surrounding atmosphere. One of the most important features in this region is the subtropical ridge. This ridge is a broad belt of relatively high pressure that often stretches across part of the Pacific. It is not a wall, but a persistent zone that influences the direction of the lower and middle atmospheric flow. Along its southern edge, winds commonly move from east to west, guiding tropical systems across warm water. Along its western side, the flow bends gradually poleward. The exact shape and strength of the ridge help determine whether a storm continues westward, curves toward the north, or turns toward the northeast. When the ridge is strong and extends far to the west, a typhoon may continue on a long track toward the Philippines, Taiwan, the South China coast, or farther inland into East Asia. When the ridge weakens or develops a break, the storm may find a path toward higher latitudes. In that case, the cyclone begins to curve, first more toward the north, then often toward the northeast. This change is known as recurvature. It does not occur because the storm chooses a new direction, but because the surrounding flow no longer pushes it steadily westward. The storm becomes caught in a different part of the atmospheric circulation. Farther poleward, westerly winds dominate. These are the prevailing winds of the middle latitudes, generally moving from west to east. When a tropical cyclone reaches the edge of this belt, its motion often accelerates and becomes more curved. The storm may still retain tropical characteristics for some time, but its path is increasingly controlled by these faster-moving currents. This transition in steering can carry a system away from the tropics and across wide stretches of ocean, including waters associated with United States territories and, in rare track arrangements, toward the west coast region of North America after major weakening or structural change. Observations indicate that a direct strike on the continental United States from a western Pacific typhoon in full tropical form is extraordinarily unlikely. Systems that affect the United States after beginning in the western Pacific generally do so after transformation and long travel across the basin. The large-scale steering pattern is three-dimensional. Winds near the surface matter, but so do winds through a deep layer of the atmosphere. Meteorologists often evaluate the average flow through much of the troposphere, which is the lower part of the atmosphere where most weather occurs. A storm that is tall and intense tends to respond to the average winds through a deeper layer than a weak or shallow disturbance. This means that the same surrounding weather map can guide different storms in slightly different ways depending on their structure. A stronger cyclone may feel a deeper current, while a weaker one may be steered more by lower-level flow. Troughs also play a major role. A trough is an elongated region of relatively low pressure, often associated with cooler air aloft and a bend in the westerly flow. When a trough approaches from the west or northwest, it can erode the edge of the subtropical ridge. This creates a weakness in the steering pattern, and the cyclone may begin to turn toward that weakness. The timing matters greatly. If the trough arrives early, the storm may curve over open water. If it arrives later, the storm may travel much farther west before turning. Small differences in timing can shift the future track by hundreds of kilometers. Because these steering features are broad and sometimes slow to change, the track of a cyclone often appears smooth when viewed over several days. Yet the atmosphere is never perfectly simple. Ridges expand and contract, troughs deepen and lift out. Nearby weather systems can alter the pressure field in subtle ways. Even small changes in the position of these larger patterns can have large effects on the path of a compact storm. Forecasting the track, therefore, depends on accurate description of the whole surrounding atmosphere, not just the cyclone itself. There are also cases in which two nearby rotating systems influence one another. This interaction is called the Fujiwara effect. When it occurs, two circulations begin to orbit around a common point, and their tracks can shift in ways that are difficult to anticipate. In the western North Pacific, where multiple disturbances may exist at the same time, this effect can complicate the steering pattern. It is not common in its strongest form, but when it appears, it reminds forecasters that a tropical cyclone does not move in isolation. The ocean beneath the storm does not usually control the direction of travel directly, but the distribution of warm and cool water can still matter indirectly because it influences storm structure and intensity. A stronger storm may extend higher into the atmosphere and become more responsive to deep layer steering. A weaker storm may remain shallower and drift in a slightly different direction. In this way, track and intensity are linked, even though they are not the same process. Observations indicate that errors in intensity forecasts can sometimes contribute to track errors through this structural connection. When a system is described as heading toward the United States, that phrase often includes a wide range of possibilities. It may refer to movement toward Guam or the Northern Mariana Islands, which lie within United States jurisdiction in the Western Pacific. It may describe a long projected curve into the open North Pacific, with later effects on shipping lanes or remote marine areas. It may also refer to the remains of a former typhoon that eventually influenced weather farther east after losing tropical structure. In each case, the atmospheric steering pattern is the first element that must be understood before rain, surge, or destructive wind can be assessed. The path through the large-scale flow must be traced. Modern forecasts rely on satellites, upper air measurements, surface observations, and numerical models to describe the steering environment. These tools reveal the position of the subtropical ridge, the approach of troughs, and the depth of the cyclone within the atmosphere. They have improved track prediction substantially over recent decades. Even so, uncertainty remains, especially at longer lead times. A small error in the placement of a ridge several days ahead can lead to a large difference in where the storm travels. Observations indicate the broad pattern with confidence, but exact motion depends on details that can evolve from hour to hour. So the storm moves within a framework of invisible currents that span oceans and latitudes. The most intense part of the cyclone occupies only a small region, compared with the size of the steering flow. Around and above it, the atmosphere arranges itself into belts, arcs, and bends of pressure and wind. These wider patterns carry the storm forward, turn it gradually, or leave it moving steadily on one heading for days. The path is therefore not an isolated feature of the cyclone alone, but a quiet expression of the larger sky through which it passes. At the top of the ocean, the surface appears simple. It reflects the sky, shifts with wind, and gathers sunlight through the day. Yet this thin upper boundary is where a tropical cyclone draws the energy that allows it to exist. The warm ocean surface is not merely a background beneath the storm. It is the immediate source of heat and moisture for the lower atmosphere, and without it the storm cannot be maintained. In the Western Pacific and across other tropical basins, the uppermost layer of the sea often stores enough solar energy to support the rise of warm, humid air over large areas. When a super typhoon forms above such water, the exchange between sea and air becomes unusually intense. Sunlight penetrates the ocean surface and warms the upper water most efficiently where the angle of the sun is high and cloud cover is not continuous. Over time, this heating creates a layer of relatively warm water near the surface. The exact depth of this layer varies with wind, currents, and mixing. But at the very top there is a direct thermal contact between ocean and atmosphere. Heat moves upward from the sea into the air by conduction at the boundary and by turbulent exchange, which is the irregular transfer caused by countless small eddies and gusts. This upward transfer warms the air just above the water and helps maintain the conditions needed for rising motion. Along with heat, the ocean surface supplies moisture. Water molecules escape from the sea into the atmosphere through evaporation. This process becomes more effective when the air above the surface is not fully saturated and when winds carry moist air away, allowing more evaporation to continue. In a developing or mature tropical cyclone, near-surface winds are often strong enough to accelerate this exchange. The faster the air moves across the water, the more effectively heat and moisture can be transferred into the storm, up to practical limits set by spray, turbulence, and the structure of the boundary layer. The result is an increasingly humid and energetic lower atmosphere. Meteorologists often refer to a sea surface temperature threshold associated with tropical cyclone development, commonly around 26 to 27 degrees Celsius. This threshold is useful, but it is not a strict dividing line. Storms do not measure a single number and then begin. What matters is whether the ocean surface and the air above it together can sustain deep convection, meaning persistent clusters of rising air and cloud growth that release latent heat. A slightly lower temperature may still support activity under favourable atmospheric conditions, while a warmer surface may fail to produce development if the air above is too dry or the winds aloft are disruptive. The warm surface is necessary, but it works in partnership with the surrounding atmosphere. In a super typhoon, the link between the storm and the warm ocean surface becomes very efficient. Air spirals inward toward the centre at low levels, moving across the sea and collecting both heat and water vapour. As this air converges and rises within the storm, the water vapour condenses into cloud droplets and rain, releasing latent heat. That heat warms the storm's core and lowers the central pressure further, which in turn strengthens the inflow near the surface. The circulation then draws even more warm, moist air from the ocean. This is the familiar feedback that helps tropical cyclones intensify. At the surface, it depends entirely on the ability of the sea to keep supplying energy. The texture of the sea surface also changes under strong wind. It becomes rougher, with countless ripples, waves, and breaking crests. This roughness increases the contact between air and water and often enhances the turbulent transfer of energy. Sea spray may be torn upward from wave tops, adding complexity to the exchange. The boundary between ocean and atmosphere becomes less like a smooth sheet and more like a shifting field of foam, droplets, and irregular motion. Even so, the essential process remains the same. The storm depends on a continuous upward flux of heat and moisture from the sea. Surface warmth is not distributed evenly, even within a favourable basin. Currents, cloud cover, rainfall, and prior storms can create patches of warmer and cooler water. A cyclone crossing a region of especially warm surface water may find more support for deep convection. A cyclone crossing cooler water often weakens, especially if the cooler conditions persist. Satellite observations and buoy measurements show that these variations matter on the scale of storm evolution. The ocean surface is not a uniform fuel tank. It is a patterned and changing field, with local differences that can influence the organization of the storm from hour to hour. Rainfall also affects the immediate surface layer. Heavy rain can cool and freshen the very top of the ocean for a short time. This thin, fresh layer may alter mixing and temporarily change the local exchange between ocean and atmosphere. Strong winds do more than increase evaporation. They also stir the surface water, drawing cooler water upward from below. This process can reduce the temperature of the sea surface beneath a moving storm. In some cases, the storm begins to weaken partly because it cools its own source of energy at the surface. The effect is strongest when the storm moves slowly or when the warm layer near the top is shallow. At the level of the surface alone, this feedback is visible as a wake of cooler water left behind by the cyclone. The air immediately above the ocean responds quickly to these surface conditions. Warm water promotes a warm, humid marine boundary layer, which is the lowest part of the atmosphere directly influenced by the sea. In this layer, friction slows the wind, turbulence mixes heat and moisture upward, and the inflowing air begins its journey toward the inner parts of the storm. The character of the sea surface therefore shapes the character of the air that enters the circulation. A warmer, moister surface supports air that is more buoyant and more capable of rising deeply once it reaches regions of convergence. Although the warm surface is essential, it does not act alone or endlessly. There are natural limits. Strong cloud cover can reduce solar heating of the sea. Repeated storms can churn the upper ocean and cool the surface over broad areas. Seasonal changes can reduce the amount of heat stored near the top. Large-scale climate patterns can shift surface warmth eastward or westward across the Pacific. Observations indicate that intense storms are most likely when warm surface conditions align with deep atmospheric moisture and favorable wind structure. The surface provides the first immediate source of energy, but its effect must be renewed and sustained. At this outermost oceanic level, the storm is still understood as an exchange across a boundary. The sea offers heat, the air accepts heat and moisture. Wind intensifies the trade between them. Nothing visible at the surface alone explains the full structure of a super typhoon. Yet the entire system depends on what happens in this thin zone where water meets air. The broad ocean has already been introduced, here at its sunlit skin. The storm finds the warm surface from which its life is continuously supplied. Beneath the bright and windmark surface of the tropical ocean, the water continues downward through a layer that appears calm from above, but remains central to the life of a powerful storm. This upper ocean is not important only because it is warm at the surface. It matters because warmth often extends below the surface through a substantial depth. That depth determines whether the sea can keep feeding a cyclone after strong winds begin to churn and disturb the water. A warm skin alone can be exhausted quickly. A warm upper layer with thickness can continue to supply heat even as the storm stirs the sea. In this deeper reserve, the ocean holds a quieter form of support for the storm above. The upper part of the ocean is often mixed by wind and waves into a layer of fairly uniform temperature and salinity. This is commonly called the mixed layer. In tropical regions, the mixed layer may extend down for several tens of meters, though its thickness varies from place to place and from season to season. Within it, water moves and blends enough that surface changes are shared downward. When sunlight warms the ocean and winds remain moderate, this layer can retain substantial heat. When a tropical cyclone crosses overhead, the mixed layer becomes the first deeper reservoir from which the sea surface can be replenished. Below the mixed layer, temperature usually begins to decline more rapidly with depth. This zone of change is called the thermocline. It marks the transition from the warm upper ocean to cooler water below. The depth of the thermocline is crucial. If it lies close to the surface, strong storm winds can more easily pull cooler water upward. The sea surface then cools, and the storm loses part of its energy source. If the thermocline lies deeper, the storm can churn the upper ocean without drawing much cold water into the surface layer. In that case, warm conditions at the top are sustained for longer, and the cyclone has a better chance of maintaining or increasing its strength. This is why meteorologists and oceanographers pay attention not only to sea surface temperature, but also to upper ocean heat content. Heat content describes the amount of thermal energy stored through a depth of water, not just at the top. Two ocean regions may show similar surface temperatures, yet one may support a storm far more effectively because its warmth extends much deeper. Observations indicate that rapid intensification, which is a swift increase in storm strength over a short period, is more likely when a cyclone passes over water with high upper ocean heat content. The deeper warmth acts as a buffer against self-induced cooling. A moving storm disturbs the ocean in several ways, Its winds push on the surface, generating waves and driving currents. They also create turbulence that mixes the upper ocean. Because the storm rotates, this mixing is not perfectly even. On one side of the track in the northern hemisphere, the combined effect of storm motion and wind rotation can produce stronger local mixing and a more pronounced upward movement of cooler water. The result is often an uneven cold wake, a trail of lowered surface temperature that remains after the storm has passed. This wake is one of the visible signs that the upper ocean has been rearranged by the cyclone. When the mixed layer is deep and warm, the cold wake tends to be weaker. The storm still stirs the sea, but the water brought upward remains relatively warm for longer. The surface therefore continues to offer heat and moisture to the atmosphere. This support is especially important for a slow-moving or very intense cyclone, since such storms have more time to churn the water beneath them. Without deeper warmth, a slow storm may begin to weaken by cooling the very water that fuels it. With deeper warmth, that weakening can be delayed or reduced. In the western North Pacific, there are regions where warm water extends well below the surface, particularly where currents and long-term heat storage create thick layers of elevated temperature. These regions do not guarantee extreme storm strength, but they reduce one of the main oceanic barriers to intensification. A cyclone travelling over such waters may encounter little immediate resistance from ocean cooling. The air-sea exchange at the surface remains strong because the surface itself is continually supported from below. What appears at first to be a surface process is therefore deeply linked to the vertical structure of the ocean. Rainfall and freshwater input can also influence the upper ocean. Heavy rain from the storm may create a thin, less salty layer near the surface, because fresher water is slightly less dense. This layer can sometimes reduce vertical mixing for a time, helping surface warmth persist. In other cases, strong winds overwhelm this effect and mix the water thoroughly anyway. The balance depends on wind strength, rainfall rate, and the pre-existing structure of the upper ocean. Observations indicate that these fine-scale effects matter in some storms, though they remain difficult to measure in detail over a wide area. Ocean currents introduce further complexity. A warm current can transport heat into the storm's path, while eddies, which are rotating pockets of water, can locally deepen or lift the thermocline. A warm core eddy contains unusual warmth extending downward and can provide a concentrated region of high heat content. A cold core eddy does the opposite, bringing cooler water closer to the surface. When a tropical cyclone crosses these features, its interaction with the ocean may change noticeably. It may strengthen over one patch of sea and weaken over another, even if the surface appears similar from satellite view alone. This remains an area where observations have improved, yet not every subsurface feature can be captured perfectly in real time. The upper ocean also responds over timescales longer than a single storm. Seasonal heating, the passage of earlier cyclones, and large-scale climate variability all shape the depth and warmth of the mixed layer. One storm may cross water recently disturbed by another and find a reduced energy supply. Another may enter a region undisturbed for weeks, where solar heating has rebuilt the upper ocean reservoir. The sea beneath the storm therefore carries a memory of earlier weather. That memory is stored not in the air, but in the temperature structure of the water. From above, the storm seems to move over a flat surface. From within the ocean, the picture is layered. Warmth occupies a depth, not just a skin. The mixed layer distributes that warmth. The thermocline limits or allows cooling from below. Currents and eddies reshape the arrangement from place to place. In this deeper upper ocean, the storm finds either sustained support or gradual resistance. The difference often determines whether the circulation overhead can continue drawing strength from the sea or begins to lose the steady supply on which it depends. Around the storm, beyond the strongest winds and outside the tightly organized core, the surrounding air holds one of the most important conditions for tropical cyclone survival. This air must be moist through a deep layer of the lower and middle atmosphere. If it is too dry, the storm struggles to maintain its tall clouds and steady release of heat. If it is humid enough, rising motion can continue with less interruption, and the storm is able to preserve the deep towers of cloud that mark a vigorous tropical system. In this broad envelope of moist tropical air, the cyclone finds the atmospheric medium through which it can breathe and grow. Humidity in meteorology refers to the amount of water vapor in the air. Near warm tropical seas, the lower atmosphere often contains abundant moisture because evaporation from the ocean is continuous. Yet the presence of moist air near the surface alone is not enough. A tropical cyclone depends on deep convection, which means strong upward currents carrying heat and moisture well above the boundary layer into the middle and upper parts of the troposphere. For this to continue, the air surrounding those rising currents must not be so dry that it weakens them. The storm therefore requires a moist environment not only at sea level, but through a thick depth of air around it. When warm, humid air rises inside a convective tower, it cools as pressure decreases with height. Cooling causes water vapor to condense into cloud droplets and ice particles, and this condensation releases latent heat. That release warms the rising parcel relative to the surrounding air and helps it continue upward. But the process is delicate. If dry air from outside the tower is drawn inward, it can mix with the moist rising air. This mixing encourages evaporation of cloud droplets, which cools the parcel and reduces its buoyancy, meaning its tendency to continue rising. The convective tower may then weaken or collapse. In this way, dry air does not need to enter the storm center directly to cause harm. It only needs to erode the efficiency of the storm's convection. In a moist tropical environment, the contrast between the inside of a rising cloud and the surrounding atmosphere is smaller. Entrainment, which is the mixing of surrounding air into a cloud, becomes less destructive because the incoming air already contains substantial water vapor. Cloud towers can therefore remain deeper and more persistent. This supports repeated bursts of convection around the storm and allows the circulation to maintain the release of heat that lowers pressure and sustains inflow. Observations from satellites and field studies indicate that storms embedded in a deep, moist envelope are more likely to intensify than storms surrounded by drier air, even when sea surface conditions appear similar. The moist environment around a super typhoon is not featureless. It includes broad inflow at lower levels, rising regions within convective clusters, and outward spreading at higher levels. Yet before reaching these more organized inner structures, the air exists as a wide reservoir surrounding the storm. This reservoir is shaped by evaporation from the sea, by the transport of tropical air along large-scale wind currents, and by the recent history of other weather systems nearby. A storm moving through air already moistened by earlier convection often finds it easier to maintain its structure. A storm encountering dry intrusions from subtropical regions or descending air from disturbed upper-level patterns may weaken even while passing over warm water. The lower and middle atmosphere also contain a property called instability. Instability means that if air is lifted, it tends to keep rising because it remains warmer or less dense than the air around it. Warm ocean surfaces help create this condition near the bottom of the atmosphere, but the full depth of instability depends on temperatures and moisture aloft as well. In tropical regions surrounding a developing storm, the air is often conditionally unstable. which means that once it becomes saturated and begins condensing moisture, it can rise vigorously. This is the foundation of thunderstorm growth within the cyclone. Moisture and instability work together. Moisture supplies the water vapor needed for heat release, while instability allows that release to translate into sustained upward motion. Cloud fields around a tropical cyclone often reveal the condition of this surrounding air. When the environment is broadly moist, outer cloud bands and convective clusters appear more continuous, and deep towers reform repeatedly. When dry air is present, clouds may look ragged, with gaps, erosion along their edges, and asymmetry in the storm's structure. Satellite water vapor imagery often shows tongues or arcs of drier air wrapping toward parts of the circulation. These dry intrusions may not destroy the storm, but they can limit intensification or cause local weakening in rain bands and inner convection. It remains uncertain in many individual cases exactly how much weakening will result, because the storm's circulation can sometimes shield its core from environmental dryness if the inner structure is already strong. The moist envelope also affects rainfall efficiency. In very humid air, falling raindrops and melting ice encounter less evaporation on the way down. More of the condensed water reaches the surface as rain, and the cooling effect from evaporation below cloud base is reduced. This helps maintain warmer conditions in parts of the inflow region and supports the continuity of convection. In drier air, by contrast, more rainfall evaporates before reaching the surface, cooling the lower atmosphere and sometimes producing downdrafts, which are descending currents of air. Strong downdrafts can interrupt the inflow of warm, moist air feeding the storm. Thus, the state of the surrounding environment influences not only cloud growth but also the character of the air returning toward the sea. Over the western Pacific, deep tropical moisture often spreads across large areas during the active season. Monsoon flow, warm waters, and persistent evaporation help maintain this humid background. This is one reason that the basin so often supports long-lived typhoons. The storm does not have to create all of its moisture locally. It moves through an atmosphere already primed with water vapor. Even so, the distribution is never perfectly uniform. Dry pockets can exist between moist regions. Air descending on the edges of subtropical high pressure can introduce dryness from above. Mid-latitude disturbances can distort the moisture field. The surrounding air remains broad and supportive on average, yet variable in detail. At this stage of the inward path, the storm is still understood through the conditions that surround it rather than through the structure of its own rotating body. The wide atmosphere around the cyclone must remain humid enough, unstable enough, and continuous enough to allow deep convection to persist. The warm sea has already supplied heat from below and through the upper ocean. Here, in the enclosing air, the energy meets a medium that either permits sustained cloud growth or gradually suppresses it. The storm's outer environment is therefore not empty space around a central machine. It is part of the machine's functioning, a deep and moist field within which the cyclone can continue to organize itself. Beyond the curved rain bands and far outside the small center that later draws most attention, a mature tropical cyclone occupies a broad field of moving air. This outer circulation is much larger than the eye or the ring of strongest winds. It spreads across hundreds of kilometers, sometimes more, and establishes the storm as a large rotating disturbance within the lower atmosphere. At this distance from the center, conditions may still appear unsettled rather than extreme. The sky may alternate between cloud layers and open gaps. The sea may already be roughening, and the wind may strengthen gradually rather than suddenly. Yet this wide envelope of rotation is one of the defining features of the cyclone. It marks the region where the pressure field begins to organize the surrounding atmosphere into a coherent, inward-turning flow. At the broadest scale, the outer circulation forms because air responds to differences in pressure. Pressure is simply the weight of the atmosphere pressing downward, and in a tropical cyclone the pressure becomes lower toward the center than in the environment around it. Air naturally moves from higher pressure toward lower pressure, but on a rotating Earth that motion is deflected by the Coriolis influence. Instead of flowing straight inward, the wind curves. Around a low-pressure center in the northern hemisphere, the resulting circulation turns counterclockwise, far from the center, where the pressure gradient is weaker. The wind is usually more moderate, closer inward, where the pressure falls more quickly with distance. The wind strengthens. This balance between inward-directed pressure force and rotational deflection is not exact at the surface because friction alters the flow. Friction with the sea slows the wind slightly and reduces the strength of the deflecting effect. As a result, the near-surface wind in the outer circulation does not move in a perfect circle. It angles gradually inward while continuing to rotate around the center. This slow inward spiral is essential. It allows air from a broad surrounding region to be collected and directed toward areas of stronger convergence nearer the middle of the storm. The outer circulation is therefore not only a ring of motion, it is a gathering system, drawing in air, moisture, and momentum from a wide marine environment. In this broad zone, the air is often organized into a boundary layer over the ocean. The boundary layer is the lowest part of the atmosphere, directly influenced by the sea surface through friction, evaporation, and turbulent mixing. As the outer circulation strengthens, the marine boundary layer becomes more active. Winds passing over the ocean lift spray, roughen the water, and increase the exchange of heat and moisture. Even before the storm's inner core arrives, the outer wind field begins to prepare the atmosphere and ocean for more intense interaction. The sea grows more irregular, and the air just above it becomes increasingly humid and turbulent. The size of the outer circulation varies greatly among storms. Some powerful cyclones have a compact wind field, with the strongest effects concentrated relatively close to the center. Others possess an enormous outer circulation that extends far from the inner core, producing widespread rough seas and strong winds over a very large area. Size and intensity are related but not identical. A storm can be very intense without being especially large, and it can be large without having the most extreme central winds. Observations indicate that the processes controlling storm size are complex and depend on environmental moisture, the history of the circulation, interaction with surrounding weather systems, and the transfer of angular momentum, which is the rotational tendency carried by moving air. It remains uncertain in many cases exactly why one storm expands greatly, while another remains compact under otherwise similar conditions. The outer circulation also influences how the storm interacts with the broader atmosphere. A wider wind field can affect larger regions of ocean surface, generate more extensive wave fields, and alter the pattern of moisture transport into and around the cyclone. It can also begin to interact more strongly with nearby weather features, including monsoon flows, subtropical ridges, and other disturbances. The storm is still embedded in the large-scale steering currents described earlier, but its own circulation now occupies enough space to modify the environment immediately around it. Moist air may be drawn inward from one sector more efficiently than from another. Bands of cloud may organize where inflow is strongest. Areas of subsiding air, meaning gently sinking air, may appear between zones of rising motion. The storm's perimeter becomes a place of structure rather than a vague edge. At this distance from the center, the vertical structure of the circulation begins to matter more clearly. Near the surface, air spirals inward. Higher in the atmosphere, some of the air that has risen within distant convective regions turns outward. The storm is not yet being described through its central core, but even in the outer circulation there is already a three-dimensional character. The lower atmosphere feeds inward, while the higher atmosphere gradually spreads away. This broad overturning pattern is weaker and less sharply defined here than nearer the centre, yet it still contributes to the maintenance of the system by linking the outer inflow to the eventual upward transport of heat and moisture. Pressure changes across the outer circulation are usually gradual. A person at sea in this region might notice a falling barometer over many hours before experiencing the most severe weather. That slow fall in pressure reflects the expanding influence of the cyclone's low-pressure centre. It is one of the quiet signs that the atmosphere is becoming more organised on a large scale. The wind may freshen steadily. Swell arriving from distant parts of the storm may begin to dominate the sea state. Cloud bands may increase in thickness and frequency. All of these changes belong to the outer circulation, where the cyclone announces itself long before the innermost region arrives. The broad wind field also affects the transfer of momentum. Momentum in this setting refers to the movement carried by the air as it rotates and spirals inward. The storm depends on that inward transport. Air entering from the outer circulation carries angular momentum towards smaller radii. As the air moves closer to the centre, changes in its path and speed help shape the strengthening ring of winds farther in. The outer circulation therefore acts as a reservoir of rotating motion, gradually feeding the inner parts of the cyclone. Without this wide intake of spiralling air, the compact core could not be sustained. Over the ocean, this large rotating envelope often appears deceptively gentle when compared with the violence nearer the centre, yet it is already highly organised, and its influence is already substantial. It lowers pressure over a broad area, strengthens surface exchange, begins to build dangerous seas, and channels moist tropical air toward the heart of the storm. It establishes the cyclone not as a single violent point, but as an atmospheric system with breadth, structure, and growing coherence. The outer circulation is the storm's first great body, the expansive rotating field within which all narrower and more intense features are later contained. Across the ocean beyond the storm's centre, the sea begins to change long before the most intense winds arrive. The first clear sign is often the swell. Swell is a train of waves that has moved away from the region where it was generated, carrying energy outward across great distances. In a large tropical cyclone, the broad outer circulation transfers momentum into the ocean surface over an immense area, and that transferred energy organizes into wave systems that continue traveling, even where local winds remain modest. The sea therefore responds to the storm at a distance. It starts to rise and fall in long, regular motions that come from far beyond the visible horizon. These waves differ from the shorter, more irregular waves created directly by nearby wind. Local wind waves tend to be steep, choppy, and closely spaced. Swell tends to be longer in wavelength, smoother in form, and more orderly. It can cross open water for hundreds or even thousands of kilometers, gradually losing energy but remaining coherent over large distances. In the outer regions of a super typhoon, the sea state, meaning the overall character of the surface, becomes a layered mixture of locally generated roughness and incoming swell from stronger winds elsewhere within the storm. Even before heavy rain bands arrive, the sea may already be rolling under the influence of energy produced far away within the same circulation. Wave generation depends on three main elements: wind speed, duration, and fetch. Fetch is the distance over which wind blows across the water in a consistent direction. A tropical cyclone provides all three in abundance over parts of its circulation. Strong winds act on the surface. They often persist for many hours, and they can extend across broad arcs of ocean. Where these conditions align, wave energy grows. The surface begins as ripples, then develops into larger wind waves, and finally into complex fields of swell radiating outward from the storm. The most energetic seas usually occur where strong winds have acted longest and most steadily, but the resulting waves do not remain confined there. They spread outward into the storm's outer surroundings. The direction of swell is shaped by the pattern of the storm's winds and by the storm's forward motion. Because a tropical cyclone is not perfectly symmetrical, the wave field is not perfectly symmetrical either. In the northern hemisphere, one side of a moving storm often combines rotational wind speed with forward motion in a way that strengthens wave growth. On the opposite side, those motions may partly oppose one another, sometimes reducing effective wind speed over the sea surface. The result is an uneven sea state, with one sector producing larger and more energetic waves. Observations from satellites, buoys, and ships indicate that the highest seas are often displaced from the geometric center of the storm and arranged according to both storm motion and wind structure. As swell moves away from the storm, it sorts itself by wavelength. Longer waves generally travel faster than shorter ones, so a distant observer may first encounter long, slow undulations, followed later by shorter and steeper components. This process gives the sea an ordered quality, even when the source storm remains violent and chaotic in detail. The ocean acts as a carrier of the storm's energy, but it also rearranges that energy according to wave physics. In this way, the outer sea becomes a record of the storm's existence, expressing its power through motion rather than through direct wind alone. The sea state in the outer circulation is not only a visual effect, it changes the exchange between ocean and atmosphere. A rougher surface increases drag, meaning the resistance between moving air and water. This tends to enhance turbulent mixing and can strengthen the transfer of momentum, heat, and moisture. Breaking waves inject sea spray into the lowest air, altering humidity and the structure of the marine boundary layer. The ocean surface becomes less like a flat plain and more like a moving terrain of troughs, crests, foam, and blown droplets. This complexity affects navigation, observation, and the storm's own interaction with the sea. For vessels at sea, the outer swell can be dangerous even when local skies are not yet severe. Long-period waves can produce deep rolling motion, strain hulls, and create hazardous conditions on decks and in harbours. Near coastlines, swell arriving in advance of the storm can lead to strong surf and dangerous currents well before the central circulation approaches. These effects belong to the outer sea response rather than to the inner destructive core, yet they are often among the earliest impacts noticed by islands and shorelines. The storm influences the ocean first, and the ocean carries that influence onward. The pattern of wave growth also reflects the size of the storm. A large cyclone with an extensive wind field can generate widespread high seas over a broad area, while a more compact cyclone may produce more concentrated extremes. Maximum wave height does not always correspond directly to the strongest central wind. It depends on how long strong winds persist over a given stretch of water and how the storm moves while generating them. This means that sea state and atmospheric intensity, though related, are not identical measures of danger. A broad storm may generate enormous swell fields even if its peak winds are somewhat lower than those of a smaller but more intense cyclone. Rain and cloud in the outer regions may obscure the sea from view, but remote sensing has shown how organized the wave field often becomes. Satellite altimeters, synthetic aperture radar, drifting buoys, and wave models reveal arcs of high sea state extending outward from tropical cyclones in ways that match the broad wind envelope described earlier. These observations indicate that the storm's oceanic reach often exceeds the area of its heavy rain and strongest gusts. The sea carries the signature farther than the clouds alone might suggest. As the swell interacts with local winds, currents, and underlying bathymetry, meaning the shape of the sea floor, the pattern can become more complicated. Over deep ocean, waves move with relative freedom, near island chains, reefs, and continental margins. They may refract, which means bend, or they may steepen and break. Energy that was organized across the open sea becomes transformed by the shallowing bottom. Yet in the outer region over open water, before those coastal effects dominate, the sea remains a large and moving field of transmitted storm energy. It rises under the influence of winds generated far away, and continues that motion with a calm appearance that hides considerable force. At this stage in the inward path, the storm is encountered not as a wall of rain or a compact ring of violent wind, but as a changed ocean. The broad circulation has already impressed itself on the surface, and the sea now answers with long trains of motion spreading outward from the core. The disturbed water is the first oceanic body surrounding the storm, ordered by wind, distance, and duration in the outer region, before the tighter bands and stronger winds draw nearer. The storm is already present in the lifted and travelling sea. Beyond the central core and inside the broad field of swell and rotating wind, the storm begins to show a more visible internal order through its outer rain bands. These bands are long, curved zones of cloud, showers, and thunderstorms that spiral inward around the cyclone. They do not form a solid wall. Instead, they appear as separated arms of weather, with wetter and drier spaces between them, in the outer portions of the storm. These bands are often the first distinctly storm-like structures to pass across sea or land. They bring alternating periods of rain, gusts, and relative calm, revealing that the cyclone is not a uniform mass, but a rotating pattern of organized convection. A rain band begins as part of the storm's broader circulation, where moist air converges and is lifted in repeating arcs. Convergence means that air flows together, and when it does so near the surface, it has nowhere to go but upward. Over warm tropical water, this lifting can trigger deep cloud growth. Because the storm is rotating, the resulting clouds and precipitation become arranged in spiral form rather than straight lines. Each band contains many smaller convective cells, which are individual towers or clusters of rising air, embedded within the larger curved structure. Some cells are vigorous and tall, with heavy rainfall and frequent lightning. Others are weaker and more stratiform, meaning more layered and steady. Together they give the band a changing, uneven character. In the outer rain bands, the weather usually comes in pulses. A vessel or island under one of these bands may experience a freshening wind, then a burst of rain, then a temporary easing as the band passes. Another band may follow later, sometimes stronger, sometimes weaker. This alternating sequence reflects the spiral layout of the storm. Between the bands, air may descend gently, drying and stabilizing the atmosphere for a time. Within the bands, air rises, condenses, and releases heat. The outer storm therefore consists of repeating zones of ascent and subsidence, which is the slow sinking of air. This pattern helps maintain the overall circulation while keeping the structure open rather than continuous. The spacing of the rain bands varies from storm to storm. Some cyclones have many outer bands spread across a large area, while others show fewer and more broken features. Their extent depends on storm size, environmental moisture, wind structure, and the history of convective bursts within the circulation. Observations indicate that outer rain bands can extend several hundred kilometers from the center, well beyond the region of strongest winds, in a very large cyclone. They may affect distant islands or marine areas long before the storm core becomes nearby. For this reason, they're often among the earliest sources of hazardous weather associated with the typhoon approaching inhabited places. The winds within outer rain bands are usually variable and gusty rather than steady at peak force. As rain falls and evaporates in parts of the band, cooler air may descend toward the surface and spread outward. These downdrafts can briefly accelerate surface wind and produce sharp changes in direction. The gusts are often stronger near the most active convective cells, where rising and descending currents exist close together. Although these winds are usually weaker than those in the inner core, they can still be dangerous, especially when combined with the rough seas, reduced visibility, and repeated squalls. Rainfall in the outer bands also shows a patchy pattern. Some areas receive brief heavy downpours, while nearby locations remain under lighter showers or only low cloud. This unevenness arises because each band is made of many convective elements at different stages of growth and decay. A fresh tower may release intense rain over a narrow area, then weaken, leaving behind broader light precipitation. New cells can form along the band while older ones dissipate. The outer band is therefore both structured and changeable, with the spiral shape persisting even as its internal parts constantly renew themselves. The outer rain bands also influence the storm's environment. They draw heat and moisture from the ocean, transport angular momentum inward, and help precondition the atmosphere for later inner core activity. Some bands serve as pathways through which air is collected and fed towards smaller radii. Others remain more detached, circulating around the storm without strongly reinforcing the center. It remains uncertain in individual cases exactly which outer bands will contribute most directly to later structural changes, because the interactions between convection, rotation, and inflow are complex. Still, observations indicate that the rain bands are not merely decorations around the storm. They are active parts of the circulation, participating in its maintenance and evolution. Over lander islands, the passage of outer rain bands often creates a deceptive rhythm. Conditions worsen, then improve for a time, then worsen again. The temporary easing between bands can make the storm seem inconsistent. Yet the overall trend remains governed by the larger circulation. Pressure may continue falling, seas may continue building, and each new band may arrive with stronger wind than the one before. In coastal regions, rainfall from repeated bands can also begin to saturate the ground before the heavier central rains arrive. This outer pattern therefore matters not only as an early sign of the storm, but as a meaningful part of its cumulative impact. At sea, the visual form of the outer bands can be striking from above. Satellite images often show white curved streaks wrapping around a darker center, separated by less cloudy gaps. These arcs are not perfectly smooth. They fracture, merge, and rebuild. Their shape reflects the broader rotation of the storm, while their texture reflects the life cycle of individual thunderstorm clusters. Radar, when available near land, reveals even more detail, showing narrow cores of heavy rain, curved lines of reflectivity, and pockets of intense convection embedded within the broader spiral. Each band is both a physical structure and a process, an organized pathway of rising moist air within the rotating system. The temperature structure within outer rain bands also differs from that of the surrounding gaps. Rising air and condensation release heat within the band, while evaporation and downdrafts may cool lower layers in certain parts. These local contrasts influence buoyancy and wind. In some cases, bands can organize miniature circulations along their length, including rotating cells or bowing segments of strong gusts. Such details are important to forecasting short-term hazards, though they remain difficult to predict exactly. The rain band is therefore an intermediate structure, larger than an individual thunderstorm but smaller than the storm as a whole. Here, closer to the cyclone than the wide sea state but still well outside the central ring, the storm becomes visibly patterned. The outer rain bands give shape to the rotating disturbance, turning broad inflow and moisture into recurring arcs of cloud and rainfall. They announce the storm in sequences rather than in a single blow. In these spiral bands, the cyclone reveals that its outer body is already organized into moving lanes of weather, each one carrying wind, rain, and rising motion around the wider circulation. Closer to the center, the spiral structure of the storm tightens. The outer bands remain behind in the broader circulation, but nearer the middle the rain bands become more compact, more continuous, and more closely tied to the central rotation. These inner rain bands occupy a region where the pressure falls more quickly with distance, where the inward flow strengthens, and where the atmosphere becomes increasingly organized around the core. The weather here is no longer marked mainly by separated squalls with wide, calmer intervals between them. Instead, the storm begins to feel more persistent. Cloud masses thicken, rainfall becomes more sustained, and the wind field shows less interruption. The cyclone is still not at its innermost ring, but it is now within the zone where the structure of the core is taking clear shape. Inner rain bands form through the same basic processes as outer bands, with convergence near the surface, rising moist air, condensation, and release of latent heat. Yet in this region, those processes occur in a more tightly wound circulation. Air spiraling inward has already travelled through much of the storm's outer environment, gathering moisture and angular momentum along the way. As it approaches smaller radii, it is forced into narrower paths. The curved bands therefore become more sharply defined and more strongly coupled to the central low pressure. Their precipitation often appears denser, and the convective towers embedded within them can rise with exceptional vigour when local conditions align. The air between the inner bands is also different from the broader gaps farther out. In the outer storm, breaks between bands may include relatively dry or only lightly clouded areas. Closer inward, the spaces between inner rain bands tend to be narrower and more humid. Subsidence, which is gentle sinking air, still occurs between rising regions, but the atmosphere remains so moist and disturbed that the contrast between band and gap becomes less pronounced. The sky often appears more uniformly overcast, with layers of cloud extending across much of the inner circulation. What changes most from one curved band to the next is the intensity of rain and wind rather than the presence or absence of cloud itself. The winds in the inner rain band region grow stronger not simply because the storm is closer to the centre, but because the pressure gradient has increased. The pressure gradient is the rate at which pressure changes across distance. Where that change becomes steeper, the force drawing air inward becomes stronger. Near the surface, friction still prevents the wind from moving in a perfect circle, so the flow continues to spiral inward while rotating around the centre in the inner bands. This spiral is tighter and faster. Gusts become more forceful, and sustained winds rise as the storm draws the air into an increasingly concentrated circulation. Rainfall in the inner rain bands tends to be heavier and more continuous than in the outer bands. The cells within them may merge into larger curved segments. producing long swathes of intense precipitation, because the surrounding air is already very moist. Less evaporation occurs below cloud base, allowing a greater fraction of condensed water to reach the surface. The rain can become dense enough to reduce visibility severely over sea and land. Embedded within this general shield, smaller convective surges may develop, producing bursts of especially heavy rain and abrupt increases in wind. These surges are short-lived in any one location, but the band as a whole continues moving around the center and inward through the circulation. Inner rain bands also play a significant mechanical role in the storm. They are not only zones of weather, they help transport heat, moisture, and momentum inward toward the central core. In particular, they can act as channels through which the storm reorganizes itself. A strong inner band may wrap tightly enough around the center to influence the size and structure of the innermost wind maximum. In some storms, new inner bands contract over time and reshape the core. This can be part of an eye wall replacement cycle, in which an outer ring of intense convection gradually overtakes an inner one. Observations indicate that such cycles are common in very intense tropical cyclones, though the exact timing and outcome remain difficult to forecast. At the stage of the inner rain bands themselves, what is most visible is a tightening of the rotating pattern and a growing concentration of energy toward the center. The vertical motion in this region is also more coherent. In the outer storm, bands may contain scattered towers of ascent mixed with broader, weak precipitation. In the inner rain bands, the upward motion often aligns more closely along the curved structure, creating a deeper and more continuous transfer of heat and moisture upward through the troposphere. This strengthens the storm's warm core, which is the region of relatively warm air aloft, produced by concentrated latent heat release. Though the warm core is not directly visible from the surface, its existence is tied to the efficiency of these inner convective processes. The bands therefore participate in building the thermal structure that supports the pressure fall at the center. At sea level, the passage through an inner rain band often brings a more relentless character than the passage through an outer one. The wind veers gradually as the band rotates through. Rain intensifies and may remain heavy for a longer time. The sea, already disturbed by swell and outer winds, becomes more confused and violent, with steep breaking waves riding over the longer underlying motion. The atmosphere feels denser with moisture. Pressure continues to fall. The storm's center is still not present, but the sense of approaching concentration becomes unmistakable in the behavior of wind and rain. Radar images near coastlines often show inner rain bands as tightly curved arcs, sometimes nearly wrapping around the center in incomplete circles. Satellite images reveal cold cloud tops where the strongest convection rises high into the atmosphere. Aircraft observations, when available, show sharp gradients in wind, moisture, and temperature across these bands. The region is dynamic and constantly renewing. Individual convective towers strengthen and weaken, but the banded structure persists because the larger circulation keeps forcing air into these preferred pathways of ascent. It remains uncertain precisely where the most intense burst within a band will occur at any moment, but the broad organization is clear and stable on the scale of the storm. In the inner rain band region, the cyclone is no longer a broad rotating disturbance with scattered arcs of weather. It has become a concentrated system with increasingly narrow structure, stronger inflow, and more persistent deep convection. The spiral pattern that began far outward is now wound close to the core, and each band carries the storm's energy inward more efficiently. Here the circulation gathers itself, not yet into the final central ring, but into the last curved lanes of cloud and rain that surround it. The storm grows denser, more continuous and more tightly organized within this inward-turning zone. Near the center of a mature tropical cyclone, the spiraling inflow of air reaches a zone where the near-surface wind becomes strongest. This region is often arranged as a tightening ring around the center rather than as a single point. Here the pressure gradient has become steep, the curvature of the flow is sharp, and the interaction between sea and atmosphere is at its most intense outside the eye wall itself. The storm has already gathered warm water from the ocean surface, drawn support from the deeper upper ocean, absorbed moisture from the surrounding tropical air, organized a wide outer circulation, built heavy seas, and tightened its spiral rain bands inward. In this smaller region, those larger processes now concentrate into a belt of maximum surface wind, where momentum, friction, evaporation, and inflow act together with unusual force. The strongest near-surface winds are not produced by one cause alone. They arise because the storm's central pressure is much lower than the pressure in the surrounding environment. Air is pulled inward by this pressure difference, but because the Earth rotates, that inward motion is bent into a tight circular path. As the air moves closer to the center, the path narrows and the speed tends to increase. Near the ocean surface, friction complicates the balance. Friction slows the air somewhat, but it also weakens the outward-acting deflection that would otherwise keep the wind in a smoother circle. Because of this, the wind crosses the pressure pattern at an inward angle. The result is a fast spiraling inflow that reaches its highest speed in a ring just outside or near the base of the deepest central convection. This maximum wind region is sometimes described in terms of the radius of maximum wind. That radius is the distance from the storm center at which the strongest average winds occur near the surface. It varies greatly from one storm to another. In compact cyclones it may be relatively small, concentrating intense wind close to the center. In larger storms it may be broader, spreading dangerous conditions across a wider area. The exact radius depends on the storm's history, the inward transport of angular momentum, and the changing structure of the inner core. Observations indicate that very intense storms often undergo adjustments in this radius over time, sometimes contracting, sometimes broadening, especially during internal structural cycles. Even so, at any given moment, the maximum surface wind region represents the belt where the sea experiences the most forceful direct action from the storm. The ocean responds immediately. Winds at this strength greatly increase surface roughness. Waves steepen, break, and interact chaotically with one another. Sea spray is torn from the tops of crests and driven into the air in dense sheets and filaments. The distinction between air and sea becomes less clear at the smallest scales, because droplets, foam, and turbulent gusts fill the boundary layer. This violent roughness enhances drag and promotes intense exchange of momentum. The moving atmosphere transfers force downward into the water, while the sea, through its roughness and spray, modifies the structure of the lowest air above it. The storm is no longer merely passing over the ocean. It is strongly coupled to it through friction and turbulence in a narrow, energetic ring. Evaporation also reaches extreme rates in this region, though the process becomes more complex than under moderate wind. Stronger wind generally encourages greater evaporation by removing moist air from immediate contact with the sea surface and replacing it with slightly drier inflowing air in the maximum wind belt. This process supplies enormous amounts of water vapor to the marine boundary layer. That moisture feeds the convection farther inward and upward, where condensation releases the latent heat central to the cyclone's warm core. Yet under the most violent conditions, abundant spray and foam alter the details of the exchange. The exact contribution of spray to heat and moisture transfer remains an active area of research. Observations indicate that it can be important, but it remains uncertain precisely how it modifies the balance in the strongest winds of every storm. The boundary layer in this region is highly turbulent. Instead of smooth flow, the air moves in eddies, streaks, and bursts. Small-scale swirls transport momentum vertically, bringing faster-moving air downward from slightly higher levels and mixing moisture upward from near the sea surface. These turbulent motions help explain why the wind at the surface arrives in powerful gusts as well as strong sustained flow. They also contribute to asymmetry. A moving storm often has a side where forward motion adds to rotational wind, making the strongest surface winds more likely there. The opposite side may still be severe, but the distribution of peak winds is often uneven. This asymmetry shapes the most dangerous marine conditions and influences where coastal impacts may become greatest if the storm approaches land. Inflow is the defining motion of this belt. Air from the broader circulation has already been curving inward for a long distance, gradually accelerating as pressure falls toward the center. In the maximum wind region, that inflow becomes most dynamically significant. It carries heat from the sea surface, moisture from evaporation, and angular momentum from the broader circulation into the innermost part of the cyclone. The air does not remain at the surface. As it approaches the core, it is forced to rise, feeding the towering central convection. This means that the strongest surface wind region is not an endpoint. It is the final low-level pathway through which the ocean and outer storm feed the vertical engine of the inner core. Pressure continues to fall inward across this ring, and the barometer records that change steadily. The gradient is now so steep that even small movements toward the center correspond to significant increases in wind and shifts in sea state. To an observer within this region, the storm ceases to feel like a sequence of bands and becomes a continuous force. Rain may still pulse, but the wind no longer relaxes meaningfully between convective features. The atmosphere is filled with spray, cloud, and fast-moving water. Visibility can drop sharply, and the sea surface becomes an irregular field of breaking crests superimposed on larger wave motion. The storm's circulation is now at its most concentrated near the surface. This region also helps determine storm surge when land is involved. Surge is the abnormal rise of sea level driven primarily by wind stress and low pressure. The strongest onshore winds within the maximum wind belt push water toward the coast and can pile it up over many hours, especially where the coastline is shallow or concave. Although surge depends on coastal shape, bathymetry, storm size, and forward speed. The maximum surface wind region provides the mechanical force that drives the water landward most effectively. Even far from land, the same force is already visible in the severe deformation of the sea surface. Aircraft reconnaissance, when available, measures this zone directly through dropsondes, radar, and flight-level wind estimates. Satellites infer it through cloud motion, microwave structure, and surface roughness signatures. Buoys and ships rarely sample the most violent part, but when they do, they confirm the intense air-sea exchange and extreme turbulence described by theory and models. Forecasting the exact strength of this belt remains difficult because small structural changes near the core can alter peak winds noticeably. Still, its general role is well established. It is the narrow marine ring where the storm most forcefully gathers energy from the ocean and channels it inward. At this stage of the inward path, the cyclone has reached the zone of strongest near-surface motion. The broad environmental setting has narrowed into a concentrated belt of violent exchange, where wind, sea, and pressure act in close balance and constant frictional adjustment. The ring of maximum surface wind is not yet the wall of deepest convection, but it is the place where the ocean feels the storm's rotational power most directly, and where the inflowing air makes its last powerful turn before rising into the central core. Inside the ring of maximum surface wind, the storm reaches the eye wall. This is the nearly circular or sometimes uneven ring of deep convection that surrounds the eye and contains the most intense combination of rain, upward motion, and destructive wind. The eye wall is not simply a wall by appearance alone. It is a dynamic band of towering clouds in which the storm's inward flowing air is forced sharply upward, carrying heat and moisture from the ocean into the upper troposphere with exceptional efficiency. In a super typhoon, this structure becomes the most concentrated expression of the cyclone's power. The larger environment and the broad circulation have already arranged the necessary conditions. Here, in the eye wall itself, those conditions are drawn into their most intense and organized form. The basic structure of the eye wall begins at low levels, where the spiraling inflow reaches the inner edge of the storm's strongest wind field. Air cannot continue moving inward indefinitely near the surface, because pressure, rotation, and convergence force it into a narrower path around the center. As more air collects in this confined region, it rises. The ascent is vigorous because the inflowing air is warm, moist, and already moving rapidly. As it climbs, water vapor condenses into cloud droplets and ice particles, releasing latent heat. This released heat warms the core aloft and helps sustain the low central pressure that continues drawing more air inward at the surface. The eye wall is therefore both a ring of weather and the central vertical engine of the storm. The clouds in the eye wall rise to great height. Their tops often reach the upper troposphere, where the air spreads outward beneath the lower stratosphere. Satellite images show these clouds as very cold at the top because temperature decreases with height through most of the troposphere. Radar and aircraft observations reveal a dense ring of intense reflectivity, indicating heavy precipitation and strong vertical development. Within that ring, however, the structure is not perfectly smooth. The eye wall contains convective towers, gaps, surges, and local asymmetries. Some sectors are more active than others. One part of the ring may show especially powerful updrafts, while another contains more descending precipitation and less vigorous ascent. Even in a highly symmetric storm, the eye wall remains a living structure of renewal rather than a fixed cylinder. Rainfall in the eye wall is usually the heaviest in the cyclone. The concentration of moisture and lift is so great that precipitation falls in thick sheets and dense bursts. Raindrops, graupel, which is soft hail-like ice, and other hydrometeors fill the cloud. Many particles are carried upward repeatedly before falling, cycling through freezing and melting layers as the convective motion continues. The result is a region of intense precipitation production and strong latent heat release. Near the surface, visibility can become extremely poor. Over land, this rain contributes to flash flooding. Over sea, it adds to the already severe difficulty of observing the storm directly. The eye wall is also where wind and pressure interact most dramatically. Surface winds near this region are already at their greatest. But within and just above the eye wall, the airflow has a pronounced vertical component as it turns upward. The strongest winds may occur near the inner edge of the eye wall at low levels, while slightly higher up the wind field can tilt and vary with height. The balance between centrifugal tendency, pressure gradient force, and vertical motion becomes extremely delicate. Small structural changes can alter peak winds or redistribute the most intense conditions around the ring. This is one reason why short-term fluctuations in intensity are difficult to predict with precision. even when the larger storm structure appears stable. The eye wall often slopes outward with height. At the surface, the ring of deepest convection lies relatively close to the eye. Higher aloft, the cloud wall extends outward, creating the classic stadium-like shape sometimes seen in aircraft and radar cross-sections. This outward slope reflects the balance of forces within the rotating storm and the way rising air curves as it ascends. The geometry matters because it separates the calm, sinking air of the eye from the violently rising air of the eye wall. The two regions lie directly beside one another, yet their motions differ sharply. At the base of the eye wall, the change between them can be abrupt. Embedded within the eye wall are individual convective bursts. These are localized surges of especially strong rising motion and precipitation. They may rotate around the eye, intensify a particular sector, or help the storm deepen if they are persistent and well aligned with the core. Microwave satellite imagery often reveals these bursts as dense clusters within the ring, and aircraft radar can track their movement and evolution. Observations indicate that such bursts are important to short-term intensity changes, though it remains uncertain exactly which ones will lead to lasting strengthening and which will simply cycle through the eye wall without major effect. The ring is continuously active, and its small-scale details remain difficult to forecast beyond short intervals. In very intense storms, the eye wall may not remain singular for long. A secondary ring of convection can sometimes form outside the original eye wall. As this outer ring strengthens, it may begin to cut off the inflow reaching the inner ring. The inner eye wall then weakens, and the outer ring contracts inward, replacing it. This process is known as an eye wall replacement cycle. During such a cycle, peak winds may temporarily decrease while the wind field broadens. Later, the storm may re-intensify if environmental conditions remain favorable. This process belongs to the eye wall because it is a reorganization of the storm's primary convective ring. It is commonly observed in strong tropical cyclones. But the timing and exact evolution vary greatly from storm to storm. The sea beneath the eye wall experiences the storm's most violent direct forcing. Wind stress is extreme, waves break chaotically, and spray fills the lowest air. Yet the eye wall is not defined by the sea alone. Its essential character lies in the transformation of low-level inflow into deep rotating ascent. Heat gathered from the ocean and stored in water vapor is released here through condensation on the largest scale within the storm. That release sustains the warm core and supports the pressure field that shapes the cyclone from the outside inward. The eye wall is therefore the storm's most efficient zone of conversion, where oceanic energy becomes atmospheric structure. To an observer crossing through it, the eye wall is a region of abrupt transition. Wind intensifies to its most severe sustained force. Rain thickens into near-constant torrents. The sky lowers into dense rotating cloud. The sea becomes indistinct beneath blowing spray and foam. Yet all of this apparent violence follows a recognizable physical arrangement. The eye wall is a ring, not a solid mass. It is a zone of ascent, not merely of wind. It is the concentrated boundary between the eye and the rest of the cyclone, where the storm's deepest convection forms a near-continuous encirclement around the center. At this point in the inward path, the cyclone has reached its principal wall of weather: the outer environment, the sea surface, the upper ocean, the moist surrounding air, the outer circulation, the wave field, the spiral bands, and the maximum wind belt all lead inward to this structure. In the eye wall, the storm takes on its most organized and most forceful expression as a ring of rising cloud and rain surrounding the central hollow. Inside the eye wall, the storm opens into the eye. After the dense ring of cloud, violent rain, and strongest sustained wind, this central region can appear unexpectedly calm. The contrast is one of the most unusual features in meteorology. The eye is not calm because the storm is weak there, and not because the circulation has failed. It is calm because the storm has become so well organized around the center that air in the middle behaves in a different way from air in the surrounding ring. Instead of rising rapidly as it does in the eye wall, the air in the eye generally sinks. As it sinks, it warms and dries, and this descending motion helps create a region with less cloud, lighter wind, and relatively stable conditions compared with the violent wall that surrounds it. The eye forms only when the storm reaches a high degree of organization. In weaker tropical cyclones, the center may remain filled with disordered cloud or uneven precipitation. As the inner circulation strengthens and the eye wall becomes more complete, the central area begins to clear. The mechanisms behind this clearing are complex, but the most important is subsidence, which is the slow descent of air from higher levels toward the surface. Air that is spread outward aloft from intense convection does not all continue away from the storm. Some of it turns inward over the center and gradually sinks. As it descends into higher pressure, it compresses and warms. This warming lowers the relative humidity, meaning the air becomes less saturated even if it still contains some moisture. Cloud droplets evaporate, and the interior becomes clearer. The eye is therefore part of the storm's warm core. A warm core means that the air in the middle levels of the cyclone is warmer than the surrounding environment at the same height. This warmth does not come from direct heating by the sun. It results mainly from the release of latent heat in the eye wall and the downward warming associated with subsiding air in the eye. Instruments carried by aircraft and drop-sondes show that temperatures inside the eye, especially above the surface, can be noticeably higher than those just outside in the eye wall region. This thermal structure helps sustain the low pressure at the surface by expanding the column of air aloft. In that sense, the apparent quiet of the eye is not separate from the storm's intensity. It is one expression of the same physical process that makes the cyclone powerful. Cloud cover within the eye varies greatly. In some storms, especially very intense ones, the eye becomes sharply defined and partly clear, with blue sky visible from below or a clean round opening visible from above. In other storms, the eye remains filled with low cloud, mist, or fragments of convection rotating across the center. The difference depends on storm intensity, eye wall structure, moisture distribution, and ongoing convective changes. A clear eye often indicates a highly organized inner core, but not every intense cyclone has a perfectly open eye at all times. Observations indicate that eye appearance can change over hours as the eye wall pulses, contracts, or undergoes replacement. The existence of the eye is a robust feature of strong cyclones, but its exact visual character remains variable. The wind within the eye is usually much lighter than in the eye wall, though it is rarely completely still. Air continues to rotate around the center, and small eddies or swirls can occur inside the eye. Near the surface, winds may be gentle to moderate compared with the surrounding storm, while higher up the motion becomes more complex. The pressure in the eye is at or near its lowest value at the surface, yet the reduced wind there reflects the structure of the circulation rather than the absence of the storm. The strongest pressure gradient lies across the eye wall, not at the exact center. As a result, the center can have the lowest pressure and yet much lighter wind than the ring just outside it. The diameter of the eye also varies. Some eyes are very small, only a few tens of kilometers across, while others are broad and expansive. Small eyes are often associated with very intense storms, though this is not a strict rule. A smaller eye means the eye wall is tightly wrapped around the center, which often corresponds to a compact and concentrated inner core. Larger eyes may occur in broader systems or during structural changes such as eye wall replacement. The size of the eye influences the experience of passing through it. A small eye may cross quickly, offering only a brief interval of reduced wind before the opposite side of the eye wall arrives. A larger eye may produce a longer calm period, with shifting low clouds and an eerie stillness over a sea that remains deeply agitated. The sea inside the eye reflects the calm only imperfectly. The wind may decrease sharply, but the ocean has already been set into motion by the surrounding storm. Waves generated by the eye wall and inner wind field continue to move through the eye, often crossing from multiple directions. The result can be a confused sea state, with large swells and steep waves interacting even under reduced local wind. From a distance, the eye is often imagined as a quiet opening in both sky and sea. In reality, the atmosphere may calm significantly while the water remains unsettled. The ocean carries memory of the surrounding violence even when the centre itself is temporarily quieter. The walls of cloud around the eye often rise with remarkable steepness. From within the eye, observers in reconnaissance aircraft sometimes see a circular enclosure of towering cloud, shaped like the inside of a giant stadium. This effect results from the outward slope of the eye wall with height. The eye itself may contain stratified layers, patches of low cloud, and slowly rotating streamers. These features show that the eye is not empty. It is a distinct inner environment with its own gentle circulations, moisture gradients, and thermal structure. The central hollow remains dynamic, even when it appears calm by comparison with the eye wall. Despite decades of aircraft observation, satellite imagery, and modelling, some details of the eye remain uncertain. Scientists understand the general roles of subsidence, warming, and structural organisation, but the fine-scale circulation within the eye and its relationship to rapid intensity changes are still studied closely. Small vortices can form along the inner edge of the eye wall and rotate around the eye. Mesovortices, which are compact rotating features within the eye or along its boundary, may influence local wind extremes and the erosion of the eye wall. Observations indicate their presence in some strong storms, but their full contribution to intensity changes and structural transitions remains uncertain because they are difficult to observe continuously. The eye therefore stands as the most inward visible region of the storm's architecture. It is central, warm, lower in pressure, and often relatively clear. It exists because the surrounding eye wall is so strong and so complete that descending air can occupy the middle. What appears at first to be an absence of storm is actually a special product of the storm's highest organisation. Inside the central hollow, the cyclone reveals its paradoxical core, a place of relative calm created by the surrounding ring of greatest violence, a quiet centre held in place by the power all around it. Within the eye wall and extending through the inner rain bands, the storm's energy is carried and transformed at a scale too small to be seen directly from afar. This inner domain is governed by cloud microphysics, the study of the tiny particles that make up clouds and precipitation, and by the thermodynamic processes that link those particles to the larger circulation. Here, water vapour, liquid droplets, and ice particles interact continuously, releasing and absorbing energy in ways that sustain the cyclone's structure. The towering clouds that define the eye wall are built from countless microscopic events, each one contributing to the storm's overall intensity. As moist air rises from the surface into the eye wall, it cools with height. When it reaches the point where the air becomes saturated, water vapour begins to condense onto small particles known as cloud condensation nuclei. These nuclei are often tiny bits of salt, dust, or other aerosols suspended in the atmosphere. Condensation forms cloud droplets, each extremely small, yet present in vast numbers. The act of condensation releases latent heat, warming the surrounding air. This warming increases buoyancy, meaning the rising air remains less dense than its surroundings and continues to ascend. In this way, the microphysical process of condensation directly fuels the vertical motion that defines the eye wall. As the rising air continues upward into colder regions, some of the cloud droplets freeze, forming ice particles. These may take the form of ice crystals, graupel, or small hail-like pellets. The exact mix depends on temperature, moisture, and the strength of upward motion. Collisions between droplets and ice particles lead to growth. Supercooled water, which is liquid water existing below freezing temperature, can freeze upon contact with ice, adding mass rapidly. These processes occur within the intense updrafts of the eye wall, where vertical speeds can be strong enough to keep particles suspended for long periods, allowing them to grow larger before eventually falling. The presence of both liquid and ice within the same cloud enhances precipitation efficiency. Ice particles can collect surrounding droplets and grow into heavier forms, which then fall more readily under gravity. As they descend, they may melt into large raindrops if they pass through warmer layers. The result is heavy rainfall at the surface, particularly in the eye wall where these processes are most active. Each falling particle represents a pathway by which water vapor has been converted into liquid or ice, and then removed from the cloud. At the same time, the latent heat released during its formation remains in the atmosphere, contributing to the storm's warm core. Not all processes release heat. Evaporation and melting absorb energy from the surrounding air. When raindrops fall into slightly drier air below cloud base, some of the water evaporates, cooling the air locally. In the eye wall, the environment is usually very moist, so evaporation below cloud base is limited compared with outer regions. This helps maintain a warmer lower atmosphere and reduces the formation of strong downdrafts that could disrupt the inflow. Higher in the cloud, melting of ice into liquid water absorbs heat, creating localized cooling layers. The balance between heating from condensation and cooling from evaporation and melting shapes the temperature profile within the eye wall. Updrafts and downdrafts within the eye wall are tightly linked to these microphysical processes. Strong updrafts carry moisture upward, supporting continued condensation and heat release. Downdrafts, though less dominant in the eye wall than in outer bands, can occur where precipitation loading becomes significant or where local evaporation cools the air. These descending currents transport momentum and cooler air downward, influencing surface wind patterns. The interplay between rising and sinking motions creates a constantly renewing structure, where no single cloud tower remains dominant for long. Instead, the eye wall persists through the collective behavior of many convective elements. The microphysical processes also influence the electrical properties of the storm. Collisions between ice particles and droplets can separate electrical charge, leading to lightning in some parts of the cyclone. In general, tropical cyclones produce less lightning than many continental storms, but bursts of electrical activity can occur in regions of especially strong convection, including parts of the eye wall or inner rain bands. These signals are sometimes used as indicators of changes in convective intensity. Observations suggest that increases in lightning may coincide with periods of structural adjustment, though the relationship is not always consistent. The distribution of particle sizes within the cloud affects how radiation interacts with the storm. Thick clouds composed of many small droplets reflect sunlight efficiently, contributing to the bright appearance of the eye wall from above. At the same time, the dense cloud layer traps outgoing infrared radiation, helping maintain warmth within the storm's core. These radiative effects are secondary compared with the dominant role of latent heat release, but they contribute to the overall energy balance. The cloud field is therefore both a mechanical and radiative structure, influencing how energy is absorbed, transformed, and emitted. Measurement of these inner processes remains challenging. Aircraft can sample temperature, humidity, and particle distributions directly, but only along limited paths. Radar reveals the distribution of precipitation and the motion of particles. But interpretation requires careful analysis. Satellites infer cloud properties from above, using visible, infrared, and microwave signals to estimate particle size and phase. Each method provides part of the picture. Yet the smallest scale interactions occur below the resolution of many instruments. It remains uncertain in detail how variations in microphysical processes translate into rapid changes in storm intensity. Models continue to improve, but the complexity of cloud-scale physics ensures that some aspects remain imperfectly resolved. Within this inner domain, the storm's energy cycle becomes clear. Heat gathered from the ocean through evaporation is carried upward as water vapor. That vapor condenses into droplets and ice, releasing heat that warms the atmosphere and strengthens the circulation. Precipitation returns water to the surface, while the heat remains in the air, maintaining the warm core. The cycle continues as long as the storm can draw in new moisture from below and sustain rising motion. Every cloud particle participates in this exchange, linking the microscopic scale to the vast rotating system that surrounds it. At this point in the inward progression, the storm is understood not only as a structure of wind and pressure, but as a field of ongoing physical transformations within cloud and precipitation. The eyewall's towering appearance arises from processes taking place at scales far smaller than can be seen directly. The strength of the cyclone depends on the efficiency of these processes, on how effectively they convert moisture into heat and organize that heat within the rotating circulation. In this inner layer of microphysics, the storm reveals its most detailed workings, where the smallest interactions support the largest motion. The innermost work of the storm cannot be seen directly in full, even when satellites view the cloud tops and aircraft enter the core. By the time the path inward reaches forecasting, the cyclone has already been traced from planetary setting to ocean basin, from steering flow to sea surface, from upper ocean heat to surrounding moisture, from broad circulation to waves, rain bands, maximum winds, eye wall, eye, and the small cloud processes that maintain its warm core. Forecasting gathers all of these layers back into a practical effort to understand where the storm is, how strong it is, how it is changing, and what danger it may pose as it approaches United States waters, islands, or coastlines. The forecast is not part of the storm itself, yet it is the most inward human response to the storm's inner structure. It attempts to read the moving system from outside to inside and to turn observation into measured expectation. Satellites provide the widest and most continuous view from orbit. Instruments monitor cloud shape, cloud top temperature, sea surface temperature, water vapor in the surrounding air, and the broad pressure and wind patterns that guide motion across the ocean. Visible imagery reveals the organization of rain bands, the symmetry of the central dense overcast, and the clarity of the eye when daylight permits. Infrared imagery continues through night, showing cold cloud tops that often mark deep convection. Microwave sensors look more deeply into the storm, revealing rain structure, eye wall replacement, and inner core asymmetry through cloud layers that ordinary visible light cannot penetrate. These satellite tools are essential because much of the tropical Pacific remains far from dense direct observation. They show the storm constantly, but always at a distance. And much of forecasting begins with learning how to interpret this distance correctly. Aircraft observations move closer, in some basins. Reconnaissance aircraft enter tropical cyclones to sample pressure, wind, temperature, humidity, and precipitation directly. Dropsondes fall through the storm and report the vertical profile of the atmosphere from high altitude to the sea surface. Onboard radar maps the eye wall, inner rain bands, and the shape of the eye in extraordinary detail. When such aircraft missions are flown into storms affecting United States interests in the Pacific, they provide information of a kind satellites cannot fully replace. They reveal the depth of the wind field, the position of the radius of maximum wind, the presence of concentric eye walls, and the thermal structure of the core. Yet even aircraft provide only paths through a vast and changing system. They sample sharply, not continuously, and the storm continues evolving between passes. Buoys, ships, island stations, and coastal radar add further pieces. Ocean buoys report pressure, wind, wave height, and sea temperature at fixed points. Ships may transmit observations, though they usually avoid the most dangerous region, islands in the Western Pacific, including United States territories, provide direct surface measurements when a storm passes nearby. Radar near land shows the curved geometry of rain bands, the contraction or expansion of the eye wall, and the progression of the strongest rain and wind toward shore. Together, these tools anchor the storm in real measurements. They prevent forecasting from becoming an exercise in images alone. Still, most intense storms remain over open ocean for much of their lives, and the observing network over water is always incomplete. What is known comes from combining sparse direct reports with broad remote sensing. Numerical models then take this information and simulate the future atmosphere and ocean. These models divide the atmosphere into a three-dimensional grid and solve equations of motion, moisture, temperature, and pressure over time. Global models describe the large-scale steering currents, subtropical ridges, troughs, and interactions with mid-latitude flow. Regional and specialized hurricane models focus more closely on the storm core, attempting to capture inner rain bands, eye wall processes, and the exchange of heat and momentum with the sea. Ocean models estimate upper ocean heat content, mixing, and the cooling wake the storm may leave behind. Because no observation system is complete, the starting state of the storm must be estimated through data assimilation, which is the process of blending measurements with model background fields to produce the best initial picture. This step is critical. A storm forecast can only be as good as the initial description on which it begins. Track forecasts have improved greatly because the large-scale steering environment is increasingly well observed and better represented in models. Forecast intensity remains harder. The path of a storm depends strongly on broad atmospheric flow, while changes in strength depend on smaller-scale processes inside the core and in the air-sea boundary. Eye wall replacement cycles, convective bursts, dry air intrusions, and subtle shifts in ocean heat content can all alter intensity on short time scales. Observations indicate these processes clearly after they happen, but forecasting exactly when they will begin or how strongly they will affect the storm remains more difficult. Thus, track and intensity are linked, yet not equally predictable. A storm may be forecast to pass near a certain island with reasonable confidence, while its peak wind at that time remains substantially uncertain. When the storm approaches United States waters or land, forecasting also expands beyond the center. the question is no longer only where the eye will go. It becomes how wide the dangerous sea state is, where surge may rise, which sectors may receive repeated rain bands, how fast the storm is moving, and whether weakening or transformation will occur before impact. A storm heading toward Guam or the Northern Mariana Islands can deliver severe wind, heavy rain, high surf, and coastal flooding even if the exact centre passes nearby rather than directly overhead. A former Western Pacific typhoon moving into the North Pacific and later influencing weather farther east presents a different problem, because the tropical core may weaken while the wave field and moisture plume continue to matter. Forecasting therefore interprets the storm according to structure, motion, and place, not by central wind alone. Uncertainty is always part of the forecast. Forecasters express this through cones of probable track, ranges of wind speed, and statements about confidence. These are not signs of weakness in method, but honest descriptions of a system that is only partly observed and inherently complex. Observations indicate where the storm is and how it behaves now. Models estimate how the surrounding environment and the inner core may evolve. Forecasters compare model guidance, recent trends, structural clues, and known biases. From this, they produce the best measured expectation possible. It remains uncertain whether a given convective burst will lead to rapid strengthening, whether a secondary eye wall will replace the first before landfall, or whether a subtle weakness in the steering ridge will turn the storm earlier than expected. The uncertainty is narrowed, not removed. Forecasting the core is therefore the final inward act. It gathers the whole storm into a disciplined form of reading. Satellites show the outer cloud field and the eye. Aircraft reveal the hidden temperature and wind structure. Buoys and radar confirm the sea and rain near the surface. Models integrate motion from the planetary scale down toward the core. All are attempts to understand a rotating heat engine moving across the ocean, shaped by layers that extend from the sun-warmed sea surface to the high outflow aloft and from the broad Pacific basin to droplets and ice inside the eye wall. The forecast does not stop the storm. It clarifies what can be known, states what remains uncertain, and translates the inner life of the cyclone into guidance for those who wait beneath its path. The storm, after all its layers have been traced inward, becomes quiet again in thought. The broad Pacific remains beneath it, carrying heat in silence. The atmosphere continues its turning, its lifting, its slow exchange between sea and sky. Clouds rise, rain falls, pressure shifts, and the warm ocean gives up energy in ways too gradual to feel from a distance, and too intricate to hold all at once in the mind. What appears immense from orbit is built from small motions of air and water, repeated without haste, shaped by the steady rules of the earth. The storm's passage leaves altered seas, cooled wakes, fresh cloud bands, and a changed sky above the islands and open water. Its strongest winds do not last forever. Its eye closes. Its clouds spread and thin. Yet the larger setting remains, with sunlight on water, moisture in the lower air, and the patient circulation of the planet continuing around it. Even the most intense cyclone belongs to that wider calm order. In the end, the storm is neither mystery nor machine alone. It is a moving pattern of warmth, rotation, water, and time. Each layer leads inward, and each inward layer returns to the same simple exchange between ocean and atmosphere. The sea gives, the air rises, the clouds gather. Then the structure loosens, and the ocean lies beneath the sky once more.